In the last lecture, we have seen stochastic integration of integrands with respect to square integrable martingale. Okay, so we have learned when integrand is m, which is a member of MC2, square integrable continuous martingale, and the integrand is a process from L star m, which is progressively measurable and also square integral with respect to m. So that process. We wish to extend this notion of integration for larger class of integrands and integrators. We have not discussed also how to integrate without using the first principle. What does it mean? I mean that the definition of integration is via the convergence, okay, and there we have used the sequence of simple processes, okay, and that is the way we have obtained this integration. So, in other words, we just know only the first principle. If you compare this integration theory with the Newtonian integration theory, that also had one first principle integration, correct? Because you take the integrand and then approximate using step function, and their integrand is just a continuous bounded continuous function, and then you take the and using the partition you get the step function, and then for that you obtain the area and the curve of the step function, and that converges to the actual integration. But that is the first principle approach to final integration. Okay, however, for integration we know there is a second approach also for classical Newtonian integration. How? That is like antiderivative. Okay, so what is antiderivative? That is obtained by using fundamental theory of calculus. What does it say? It says that if you integrate the derivative of a function, then you get the function back. So here also one can ask the same question. Okay, I understand the definition of integration, but how can you calculate easily using some sort of theorem which is like fundamental theorem of calculus here? So we have not discussed that yet. So we seek for a formula analogous to the fundamental theory of calculus, okay, and that formula we call Ito's formula. So that gives our ability to find out integration from a formula, okay, without going to the first principle. Okay. Now let us start definition. Okay, so this is a definition of a larger class of processes which need not be a martingale. However, a martingale is also a subclass of this. Okay, so this subsumes the class of square integrable martingales. Here we call this is a local martingale. So let us start. Let M be a process which is written as m subscript t, t is 0 or more than 0 positive. So this is an ft adapted process with starting 0. Okay, m0 is equal to 0. You remember that was also the constraint we put for denoting script m2 and m2c. So if there exists a sequence of non-decreasing family of random variables Tn, n is equal to 1 to infinity, of ft stopping times such that it grows to infinity with probability 1. Okay, if you look at the limit, so limit is infinity with probability 1, and with the help of this Tn, if we construct this stopped process m subscript small t minimum capital Tn, what is the meaning of this? This meaning of this is that the value of this process at time small t would be exactly as mt if capital Tn is more than t. However, for some realization when small t is more than capital Tn, that means that okay, capital Tn is smaller than small t, then we are going to choose only m at capital Tn. So minimum of t and capital Tn we are going to choose, okay, and that would be my m superscript nt. Now for every n, okay, I am going to get one such stochastic process. Now my stochastic m is such that there exists a sequence of increasing stopping times Tn, so that this derived new sequence of processes for every member n, we are going to get a martingale. Okay, the m is a ft martingale. Okay, so this is an ft martingale for each and every n. So you have actually sequence of processes, but for every n you get a process, and that process is a martingale. Then we say that this m is a local martingale. and we denote the class of all local martingales as script M-loc. And if M is continuous in addition to be a local martingale, we call that M is a continuous local martingale, and that subclass we denote by script M C comma loc. Okay, so M C comma loc is a subclass of M loc. Now for this we would like to define what is quadratic variation, okay, covariation of such processes. Okay, so now we recall that what was the definition of covariation and quadratic variation. For quadratic variation, we actually use the Dubs-Meyer decomposition, that given M as a square integrable martingale, there with M square we look at the Dubs-Meyer decomposition, then the natural adapted increasing process was taken as the quadratic variation. But here when M and N are two continuous local martingales, their square integrability is not assured. Okay, however, we generalize the notion of quadratic variation here. So this theorem, this statement says that, so there is a theorem which asserts that existence of a unique adapted continuous process of bounded variation, okay, A, such that A starts from 0 and the product of the process M and N minus subtracted A, so that is a continuous local martingale. Okay. So since M and N, neither of them could be square integrable, so I cannot assume that this difference would also be square integrable. Okay. However, since it is MC log, I can look for Mn minus A is an MC log. Okay, the continuous local martingale, and if that is the case, then we denote this A as quadratic covariation of M and N. Okay, and if I have M and N both identical, then the quadratic variation coefficient of M and M, that is called quadratic variation of M, we also denote by only writing M here. This condition is coming straight from the generalization of the Dubs-Meyer decomposition. There we had Mn, okay, is equal to a martingale and plus some boundary variation process, square integral martingale and boundary variation process. Here and then if we subtract, we get a square integral martingale, but here we cannot expect, so we are just asking the difference is just continuous local martingale. Okay, so here let us also clarify this issue, that whether this notation is a generalization, this coincides with the notation and definition what we have done before. Yes, because square integral continuous martingale is also continuous local martingale. Why is it local martingale? Because you can choose Tn is equal to exactly n, or deterministic, and then you are going to get that, okay, that satisfies these conditions, and you are going to get that this is a subset of that. Next, what we do is that we try to develop the notion of integration with respect to local martingale. If M is local martingale, continuous local martingale, and is a bounded variation, then M is identically 0. So this is also extension of the result what we have actually proved in earlier class. Okay, so where M was MC2 square integrable continuous martingale, so that is a special class of this class. So for the special class we have obtained this result, but this result is also true, this conclusion is also true for a general class, that if we have a continuous local martingale and bounded, and it is a bounded variation, it is actually a trivial martingale. Now we define a even larger class of stochastic processes which we call as a semi-martingale. So what is semi-martingale? Semi-martingale is an FT adapted process. Why I am saying always FT adapted? That means even without specifying each and every time, I always assume that there is a filter probability space in our hand already. So omega FP is the probability space and FT is the filtration there. So given, and we fix that filtration. Okay, and X is FT adapted process and has the following decomposition. What is the decomposition? The XT is written X0, which is just a random variable, F0 measurable, and we have MT. MT is a continuous local martingale, and AT is a continuous adapted process of bounded variation. okay, on every finite time interval. Why finite time interval? Because even if you take a very nice, increasing process, say at is equal to t, just, but its total bounded variation will be infinity if you take whole close 0 to infinity. Okay, so when we make a finite interval on that time interval, if we compute the total variation, then we are going to get finite. Okay, so bounded variation on finite interval. So this is xt is a semi-martingale. We are going to use this term quite frequently for this lecture and one or two next, because this is the more general process we are going to discuss. Okay, so next we talk about the uniqueness of the decomposition. If X is a continuous semi-martingale with with two different decompositions, for example, X naught plus MT plus AT, another is the X naught plus M bar T plus A bar T, then where this M and M bar both are local martingale, continuous local martingales, and A and A bar are both finite variation process on compacts. So basically, we're saying that, okay, two different decompositions, okay, same decompositions. Then this M and M bar would be equal with probability 1, and A and A bar would also be equal with probability. That means they are indistinguishable. Now we describe how do we actually go for integrating with respect to a continuous local martingale. If M is in MC-loc, continuous local martingale, we would consider then for the class of integrands, this class X is measurable and adapted, okay, and the probability that this integration xt square dmt 0 to t is finite with probability 1. Okay, remember that when we have obtained the class L of M, then we have taken expectation of this random variable and we have required that expectation to be finite. However, here that is a very strong condition to impose. Why is it so? Because my M is such that, okay, M is just a continuous local martingale, so it is I might not have that expectation to be finite of this thing. Okay, however, I can just require this to be finite valued random variable. Okay, if some random variable has expectation finite, that implies that the random variable is finite valued. Okay, but the reverse is not true. I just have finite valued random variable, that means real valued random variable. Okay, it could be anything, it need not be in L1, L2. Okay, so the probability of this random variable is finite is 1. So that type of processes we just gather and make this class script P. Okay, and then in that class we would of course take the quotient with respect to the equivalence relation of indistinguishability, so that two different processes which are indistinguishable should be identified as a one single object. So that is the class P. And P star, this star is actually resembling with the L M and L star M, as we have introduced in the earlier lecture, for the case when we consider the integrand for square root continuous square integrable martingale. Here for continuous local martingale we have P and P star. Here X should be in P, however X is progressively measurable, and then you take the quotient. If M is a continuous square integrable martingale, and then we have that Lm, as I have described earlier. Here you had expectation of this thing was finite. Okay, so that implies that, okay, this is also finite. So therefore Lm is a subset of P and L star is a subset of P star. So this is a generalization we understand. Okay, so if M is in MC-loc, okay, so continuous local martingale, so then there exists a non-decreasing sequence of Sn, okay, of stopping times, such that this following result holds. What is that? That the stopped process is square integrable continuous martingale. So now, let me clarify. Given a continuous local martingale, we know that there exists, of course, a sequence of stopping time, okay, for which this stop process will become a continuous martingale. But this is telling something more, okay. This result is saying that I can choose the sequence of stopping time, increasing stopping time, such that the stop process becomes square integrable continuous martingale, okay. For definition of local martingale, you just need that stop process becomes a martingale, correct. Here we are asserting that we can further choose a stop sequence of stopping time such that this becomes square integral continuous martingale, okay. Next result is that for x is in p star, okay, p star as it is defined in the third point, construct a sequence of stopping times. So what is this stopping time? We are considering, say, x square is dms, m is here is quadratic variation 0 to t, and when it is more than n. So you understand that we are looking at this criteria actually, that finite should be property 1, okay. Now if it is crossing a large number n, okay, and then we are checking that at which time it is crossing that n, okay. So wherever it is crossing that n, that time, that I am recording Rn, okay. However, if this time is too large, okay, then we might run into some problem, technical problem. So we are taking minimum with n also. So if this integration becomes larger than n before time t is equal to n, then that time would be Rn. If it takes longer time than n, then I am going to take n as this, okay. So Rn has this property that as n tends to infinity, because if you take larger and larger n, we know that for t is equal to 0, it is 0 left hand side. So it would take more longer time to cross the threshold n, and then this Rn would increase to infinity, okay. So then the Rn goes to infinity as n tends to infinity, okay. So actually these are results. So these results are not very immediate or obvious, it needs proof. However, we are just stating these results here. Then Rn tends to infinity as n tends to infinity. Next, we consider the minimum of Sn and Rn. So let us see again what is Sn. Sn was a localization of the martingale. See, we call localization, correct, because there we are stopping it so that we are preventing m to fly away, okay. And then that means we are localizing that, okay. So that is the reason of the name of localization, and this Sn is the sequence which is localizing the integrator. Here Rn is on the other hand is actually helping to localize the integrand, okay, in the sense that this with respect to this martingale integration, so that these things remains bounded. So with Rn and Sn together, we want to retain both the properties, so we take minimum of Sn and Rn, okay, that we call as Tn. So Tn is such that both the properties do hold, that integration of x square with respect to quadratic variation, that also remains bounded, and also that mnt, okay. So this also becomes a square integrable continuous martingale, okay, and the integrand we choose as xt, okay, for all time till Tn, okay. After Tn we are going to kill that would be just 0, okay. So that is the kind of localization we are doing. Now from previous construction Sn and Rn, we know that, okay, Xn is square integrable continuous martingale, and Xn, the way it is constructed, is also in L star of Mn. Why L star? Because this process started with this adapted and continuous for this, and then then you get that L star of M, progressively measurable. This is actually not continuous, this is actually left continuous, correct. So if it is adapted and either left or right continuous, okay, so then you get that it is progressively measurable. So thus now we can actually integrate this process with respect to this martingale. Okay, both are actually different from our original integrand and integrator. However, with these approximations, okay, we can talk about the integration exactly the notion what we have defined earlier. Okay, so we construct this sequence of integrands. So for every n we are going to get one integration. Okay, that integration itself is also a function of t, correct? That itself is also a stochastic process. So this is well defined for each and every n more than or equals to n. So also for this is another nice property, when m is more than n. Okay, so we have it, mn, xn, but now I am having m which is more than small n. Okay, and we are constructing xm. So what would happen? So here this tn would be replaced by tm, that would be, you know, that would be survive for a longer time and then become 0. But that if I look only time t is equal to 0 to tn, okay, even I have killed later, but I am looking only for the beginning time, that would coincide, the beginning time would coincide with the exactly xn. Okay, and therefore when small t is between 0 to capital Tn, then these two processes has identical values. On the other hand, if you look at mn and mm, they would also have identical values for every t between 0 to tn. Okay, so we are going to get both the integrals are exactly same for every t between 0 to tn. So this is a very useful observation. Why is it so? Because that would give us a notion of convergence, correct? Because, you know, when I am observing one n and then n plus 1 onward, that value of the stochastic integral is not changing on the interval 0 to tn. However, as n is larger, this tn is also going to infinity, correct? So for a given small t, I can look for one n onwards, so where it is where t is more than t, and then the stochastic integral value is not going to change further. Okay, so let us define from this observation that imtx is defined as itmnxn for some n such that tn is more than t. So what does it mean? So let me clarify again. So here one should remember that tn is a random variable, but t is deterministic. So what does it mean? So given a small t fixed, I am looking at some particular omega. For that particular omega, I know that sequence of t and omega is going to infinity. So after a large n, it should cross small t. Okay, so whenever you cross, okay, that I am going to put that, okay, that n, and then with that n we can actually construct this, you know, stochastic integration, and whatever it is that I am going to declare as this. Okay, so for every omega we can do that way. Okay, so this n is also you know, random variable, correct? Because, you know, the n for which tn is exceeding t, that is also a random variable. Okay, so I mean, it is not that I am saying that I mean, one can find on a deterministic n and then it remains. No, it is not. I mean, n is also a random variable satisfying this. However, that random variable is finite, is not infinity. Why? Because tn goes to infinity almost surely. So for every small t, for every omega, we are going to get a finite n, and that we are going to plug in here. Okay, and then we don't need to worry. Then that n onward every time, okay, the stochastic integrals would be the same value. Next, we say consider m is a continuous local martingale and x is in p star. Okay, then the im x as it is defined here. Okay, so here this is the stochastic process with respect to time t. So this stochastic process is also in MC-loc. It is also a local martingale, continuous local martingale. So remember what we have done earlier, that we have considered square integrable martingale here, and then we have defined the stochastic integration to be a square integral martingale satisfying certain things, correct? But here we are not doing that way. We are cooking up this limit, okay, this stochastic integration, and we need to therefore cross check that whether this is really in this class. Okay, so this is a result that yes, of course, after obtaining this stochastic integration of IMTX, okay, this process is also a local martingale, okay, with continuous path almost surely. Okay, so what did we get? We got that, okay, I am, okay, this functional is I mean the I is functional, okay, for x in P star, okay, for a given local continuous local martingale we are getting another continuous local martingale. Okay, now there are some other properties. So this property is also true for a special class which we have already seen earlier, that if I have quadratic covariation of this stochastic integral with respect to another local martingale. Okay, in earlier discussion we had all the places square integral martingale, but now we have continuous local martingale. So if we have a continuous local martingale here, and phi is integration of x with respect to another continuous local martingale m, then the quadratic variation of that is x, this integrand, and the integrator is quadratic variation of m, this m and this n. Okay, m and this n, and this is true for all m in MC log. Okay, so this is also another characterization. I mean, no other process satisfies this condition. Okay, so the stochastic integration of x with respect to m is the only process for which you get this identity. So this is also another result, that let m is a continuous local martingale and x is in P star. So then there exists a sequence of xn from the simple processes such that for every time capital T positive, okay, as n tends to infinity, this approximation, I mean this difference, okay, xn minus x whole square, and with respect to integration with respect to the quadratic variation dmt, that goes to 0 almost surely. Okay, so earlier what did we have? We had that this used to go to 0 in L1, correct, because the expectation of this is to go to 0. Okay, so that was the box norm. Here this result is more stronger than stronger than the earlier result. It is saying that, okay, if I have x from P star, and then I can choose a sequence of simple processes, so that without taking expectation, okay, so just this random variable itself, which is the integration 0 to capital T for a fixed capital T, and this integration is with respect to quadratic variation of m. So this random variable goes to 0 almost surely. And then for integration, corresponding integration, that itxn and itx, you take the difference. So earlier what we had shown is that expectation of this square, okay, that goes to 0. Okay, but here we have stronger result, that, okay, if we consider the subnorm of that, that also converges to 0 almost surely. Okay, so it converges so uniformly almost surely, right? Subnorm is going to 0, correct? So this as a function of t, and is also another function of t, we take the subnorm, the difference, and that goes to 0.